Okay, thank you, Magnus, for the kind introduction. Not always you get so nice words from your students. Right. The purpose of my talk is to be introducing maybe the technical discussions tomorrow. Maybe I feel a little bit about as a party pooper here to say what are the difficulties with all the visions that we have here. And I think on the other hand, from an academic perspective, we need something to do research on. We need hard and difficult questions. And the title of the talk is about society-scale cyber-physical systems, and I will challenge a little bit the sort of vision of Eric here, and to understand what exponential growth, and Preben actually mentioned this. What is an exponential growth? I mean, we know that in nature nothing grows exponentially. At the end, we run out of something. We run out of the bacteria on the petri dish, run out of food. Economic systems run out of money or energy or something. So so that's what we try to discuss. So the talk will be very much about scalability issues. So I will discuss very brief my view on basically the previous talk, so I can skip quickly past that. Discuss scalability and what does it mean to the new types of systems where the real world and the cyber world interact. Network society, my view on these things is that we've seen three types of technical revolutions, and we have been the Internet of Information has been around. We move information around across the globe at light speed, so information is available anytime, anywhere, and that has created tremendous overturn of the industry that used to have an information monopoly. I mean, like the banks, the travel agents, they had information that the user didn't have. Now everyone has access to all the booking information of all the airlines. So you skip a lot of middlemen that dealt with information. Now we move from the cyber world into the real world and the Internet of Things. So we collect a lot of data through sensors, and there's a massive amounts of information available, and we can make business use of that in a very effective way, as we've seen in the previous talk. And we are now on the brink of taking the final step to actually not only to measure but also to physically interact with the physical world. We call that the Internet of Control. So that's we actually want to influence the real world through the cyber world, and that is what we call the real meaning of cyber physical systems. Internet of sensors and big data we have seen for some time. Can skip these. This is then the Internet of Control. We want to control the factory, control the energy system. We want to control the crane in the harbor. Maybe remotely drive the car, remote surgery, and the excavator, and all these things. And this control can be either by people or machines. And that's the thing we want to do. And cyber physical systems are traditionally things where computers interact with the real world, and traditionally this is home appliances. We call them embedded systems when they're standalone. But the step we want to make now is to go to society scale. We want to discuss networked embedded systems that can control society scale systems like the traffic system or the energy system, or so it's going to be going from single devices to millions or billions of devices that potentially interact. And that, of course, puts the finger on, does it scale? I would say we can do all these things, but the big question is, can we afford it? Do we have the money and the energy to do all these things? And so why is it important? Well, if you look at some of the sort of medium scale type of application of cyber physical system, we want to control this petroleum plant or this car manufacturing plant. I would say this is medium size because it's still rather low volumes. There are not so many car plants around in the world. But the nice thing is that every car plant, if you can digitize it, you can make a lot of money by making it more efficient. So there's millions of dollars at stake for every plant, which means that it's quite okay to tailor make a digital solution for that particular plant. You can handcraft a solution. You can put some 100 consultants that program for a year, and you can make lots of money by doing this. But then, if you go to the society scale, let me take an example here: the smart home. There are millions, there are hundreds of millions of homes out there, and if you want to make them digitized, you cannot handcraft it because there are now tens of dollars at stake. That's the energy you can save in a year. You can't have 100 consultants in your home that program your home. So it has to be a completely different solution. It has to be scalable. It has to be standardized solution because you have in order to handle these massive volumes. Otherwise, it won't happen. And how do we standardize things? Well, in economics or in techno-economics, we talk about dominant designs, and there are lots of dominant designs in history, and you all recognize them: the PC, the versus the Commodore, the Windows against CPM, and LTE against WiMAX, and all these things that were successful because they are worldwide available, and there are billions of devices. And what characterized those? Well, dominant designs in ICT are typically flexible. They are multi-purpose devices. You can use them for many things, and they're usually multi-vendors. So you can buy them from basically the same. I mean, you can buy a PC from almost all vendors, and they behave the same way, and you can use the same software. And if you look at the roadkills, they're single purpose usually. They do one thing. The DVB-H system is a very nice example. You can only watch TV, and usually call them one-trick ponies then. And there are usually few vendors, and these are examples of things that don't go down very well. If you look at the dominant design currently in ICT, what are the standardized platforms for providing ICT services? I think we have now a very, very strong dominant design, and the dominant design is called IP and cloud. That's the dominant design for all types of mobile and all kinds of ICT solutions, I would say. And they're very nice because IP has created a very simple interface for connectivity, and that creates an explosive growth, and it works on all platforms. Any tablet, any smartphone, any PC, anything can use. You can use all the applications on any platform. And the trend we see now is about software-defined networking and virtualization. Are basically the same thing. They create a lot of flexibility. And how do we? What is the main trend that we see from a technology perspective? Well, what we've done here compared to the plain old telephone systems and GSM systems is basically that we have taken traded performance for flexibility. We have gotten a system that is extremely inefficient for everything, but equally inefficient for everything. But extremely flexible. It can be used anywhere. But from an engineering perspective, it wastes energy, it wastes time, it wastes overhead. It does lots of overhead. Every IP packet that is transmitted out there, there's a minute content that is actually payload, but information that people actually out there. But we do all this because of it's extremely flexible. And you can say that transparency eats efficiency for breakfast. So it's very important that we are transparent. And the consequences, of course, that we let's say in the app domain here, that a very good example of how this works, that the standardized platform IP and the App Store, or the two the two dominant operating systems on smartphone, iOS and the Android platforms, means that you can, in a second, after you created your app, it's available to millions of users everywhere in the world, because most people can understand English, and so it's a huge global market that has opened. The bad thing is, of course, that there are millions of others that won't compete with you. So you have a big opportunity, but the competition is fierce, and things go very, very fast. From the minute you deploy an app, it's probably outdated within, and it's completely worthless within a few months. So it's a very, very short cycles here. So the question is, this is a success story. We're very good at providing apps on standardized platforms all over the world very, very quickly. So the question is, does this work for cyber-physical systems as well, as it does for I listed what I think are the four key success factors for the Internet of Information. We do have a dominant design for computing and communication platforms. So there's in the cyber world, we have everything standardized, and every smartphone, thanks to every Android smartphone looks the same. We have almost free internet, or let's say zero marginal cost internet. You pay monthly fee, and then the extra bit that you transmit is basically for free. Affordable equipment, anyone can afford a smartphone. And so the question is, does this work also for the cyber physical world? Well, yes, we have those things. Affordable equipment for the cyber physical world, yeah, questionable. If I want to put a sensor in my bike or on my dog tag, is that can I afford $500 smartphone to put there? No, it has to be some different types of devices that are much cheaper. If I want to rig my home, I can't afford putting smartphones everywhere. It has to be much cheaper platform. So that's something that needs to be discussed, and it is being discussed. But here is the real showstopper. That damn physical world looks different everywhere. It doesn't, it's very nice. The cyber world, we can create an environment, a platform that looks the same everywhere in the world. But the real world, my home looks very different from your home and from your home. And so that's where we're back to this today, to the tailor making of software applications. So the real challenge that we see now in research is to see we have this very convenient hornet's waste in communication, which is IP. That is, of course, a bottleneck in communications. But from a standardization point of view, this is very beautiful, because there's a simple interface here. But the question is, can we repeat the story? Is there some other abstraction than the IP abstraction that could work for the cyber physical world? Right now it looks bad, because most standards for the cyber physical world, they actually seem to be growing instead of shrinking. I mean, because you add additional features and new sensor readings that should be included in the standard, so they actually seems to be expanding rather than shrinking to make it more scalable. And the problem is, of course, that cyber physical systems is something very different from the cyber systems that we have, because there is a vast amount of possible applications with a vast range of requirements. It can be anything. We can have all types of technical requirements could look very different depending on whether they are human-centric or machine-centric. And in the machine-centric types of world, it actually can have a vast range there as well. Sometimes wide area coverage is important. Sometimes it's not. Sometimes cost is important. If I want to put 100 sensors in my home, cost is very important. If I want to put 100 sensors in a billion-dollar factory, it doesn't matter. It's more the deployment cost that is the important thing. And this has been addressed in the 5G development. This is a Metis picture, and we can see the particularly interesting directions are the machine type communication direction. We see this massive machine type communication, which is basically what I call the Internet of sensors, and this is the Internet of Control direction, and here. Here it's mainly lots of devices, very cheap energy and cost, and there it's very low, very high performance on the upper side here. Yeah, we can. So the problem that we've seen in the previous in design phases, that what we've done here in the old days, we created systems. Basically, circuit switch systems with very high quality of service. The plain old telephone system, with all this deficiency, at least had no delay. There was basically no delay because of the physical connection from point A to B, and it definitely had quality of service guarantees. And what we've done as we go to the packet switched IP world, we've moved in this direction. We've gone to best effort and we degraded the performance, but we've gained this multi-purpose software defined. It could be transparent and flexible, whereas we don't have these features over here. So we have gone very far in this direction. So what we want to do now to do these time-critical applications, we somehow have to go back. And the question is, how can we do that? Yeah. The current paradigm has no problems in this area. The only thing we have problems here with is maybe energy consumption and SIM cards that needs to be replaced with something else. But that's not the big problem. The key problems are over here in the critical MC. The IP cloud paradigm doesn't work here. If you want the 5 milliseconds delay or the very low delays, it doesn't really work here. So the question is, do we need to build a new infrastructure for this that can handle these things or not? That's an interesting question. And here is the reason why it doesn't work. But this is the way. Let's assume that we want to do want to fly this model aircraft remotely using LTE and cloud, and we want, in order to be able to fly the plane, really, we need a millisecond delay in order to be able to counter every gust of wind and anything like that. What the pilot does by the force he feels in the rudder, in the stick of the plane. So now, if we want to do this using a cloud solution, and we want, let's say, less than 1 millisecond delay, the physical distance to the cloud server has to be less than 150 kilometers. So we cannot have the cloud in Luleå in the north of Sweden and fly the plane here, because then the speed of light alone will not be sufficient. So we need to do something else. And there are basically two ways what we can do. We can do things on the edge here that was mentioned before by Ali on the you can do edge computing inside the network, or we can do autonomous processing. The plane itself can do the computing. This is actually how drones are flown from New Mexico and in the Middle East, because they're not flown by they're not piloted by the controller. They actually the guy tells them what altitude and what direction they should fly, and the plane itself does the flying. Counters counters all the turbulence and things like that the plane may encounter. So this is also very an important question from a business perspective. Is this inside or outside the network? This is something that the operator would provide. This is something that the plane, the end user would provide. So that's quite interesting question on what type of services can we provide here. So to sum up here, if you look at where are we going right now, and what are the sort of possible ways to go. If we want to do these really high quality, very low delay applications, we can go on the axis of between performance and flexibility here. We can use the current paradigm, or we can go back to the plain old telephone system, or basically dedicated connectivity for each application. We can do application-specific design. And then we need a killer application because we can't build an infrastructure for one application, because that, I've seen this before, that has to be very, very good application. Even TV didn't cut it, so it has to be something really, really important that we can build an infrastructure for a simple application. We can go in this direction, and then we say, okay, the IP cloud has only best effort, so we need a lot of autonomy. It cannot provide us very much real-time connectivity. It may can give us tens or hundreds of milliseconds, but we have to live with that. So there needs to be a lot of autonomy on the outside. Or the billion-dollar 5G question is, what can we do in the middle? Can we actually add on to this to get somewhere in the middle here, to get something that is sufficiently better in performance, but still maintains the reasonable flexibility to make it fly from a business perspective? It has to attract enough applications to pay for the infrastructure, and that is, I would say, the billion-dollar question. There is the valley of death, and there is the budget alternative, and so the billion-dollar question: what is sufficient? And that I think quite many research projects now, including 5GPP efforts, are trying to determine what is sufficient here, what should be included in the network, and what should be done outside the network. And of course, it's an interesting discussion for operators. Of course, operators want to put more in the network to provide more advanced services, but the question is there anyone that wants to buy those services? And there's always the big issue about safety. If we want to fly planes and cars and things like that, do we want to fly in a plane that is automatically piloted? Probably, planes have been able. You have been able to fly planes automatically for many years, but you still have two guys in the front there that look comforting and look as they know what they're doing, so this is, I think, is a real big issue of the Internet of Control. Do we want the things around us that can possibly damage us as persons? Do we want them to be remotely controlled? This is also, from a security and a reliability perspective, a very, very important question. And I think that's not only a question about technology. That is basically a question of trust, which is at the end is a political issue. Who is responsible when the automated car crashes? And maybe Kalle will discuss this and Ulf will discuss this afternoon. Finally, just a quick word about another option that we haven't really tapped in, and this is just, I throw this out as a question, and I hope that can be some discussion about this. And what about the data that is out there? And I think this is we have just trying to tap on this. And there's some big actors like Facebook and Google that have been in this business for a while, to collect data and use it and refine it and to sell it. And in the last year's Johannesberg conference, we had a talk from here that sold refined geodata or location information for users. And so the question is, what will this market look like? I think to make really big use of many of the IoT applications and cyber physical system applications, we need to collect data from other sources than we've collected ourselves. So what will be the business models for selling and buying this data, and what is the sort of the optimal half-baked analyzed material that you can buy? Is there something like a bake-off in big data that is sort of not the raw material but already compressed and refined data that you can buy to use for different purposes? And I think this will be a huge market out there, but we still don't see the business models and how this is going to be automated. So finally, as concluding here, I think the societal scale cyber-physical systems is really the next leap in digitization in society. And but they are as we go from millions to billions of users and devices, this is not always clear-cut how it's going to be done, because there are severe sort of scalability issues and cost and energy, and also in network performance that we need to deal with. And the dominant ICT solutions, IP and cloud, do only solve part of these problems today at a limited scale, and they have these performance issues that we need to deal with somehow. So the question is: new infrastructure, incremental improvement, or just keep on doing and be more autonomous? That is basically the path that I see. And what we definitely need to make this fly is a new generation of standards and interfaces for the cyber-physical world. How can we standardize cyber-physical interfaces? I think that is the real. Can we do a app store for CPS? That is really the big challenge that we see. And then both these, the app store paradigm and the scalable infrastructure, both these things are needed to make society scale CPS fly. Thank you. Mm-hmm. Mm-hmm.
So we are a little bit late for coffee, but we still have time for a question or two.
Hello, Martin Thorngren, KTH. Thank you, Jens, for an interesting talk. I'm glad you brought up safety in the end. Mm-hmm. I think the implications are larger because we have things like certification, safety standards and practices that will have very large implications on how you develop systems, and you touched upon liability, I think.
Yeah.
So that's a very important aspect when the cyber and physical world meets, and which are pretty much unresolved.
Yeah, I absolutely agree. I mean, you can take the airline industry as a really good example on the long lead times between when you actually introduce new technology until it's actually you're able to use it in airplanes. It takes tens of years. I mean, for instance, I mean, I would usually take the fly-by-wire situation that you replace hydraulic steering of an airplane with electrical wires. I mean, that took decades just to make sure. I mean, as you say, it's a matter of trust. And in the long run, it's a regulation, and it's a political issue that needs to be. But we will hear a little bit more about that from the transport industry side, and see what are the issues there.
Yeah. Okay, let's take the two final questions here. So perhaps you can go first.
Thank you. Yeah, about this mission critical services, and as you pointed out, that due to the physical nature, the range, like 1 millisecond extreme latency, could limit the distance. If we consider the processing delay, then it could be even smaller. But of course, we can find these applications like this mining in the mining industry, that in some environment that could be hazardous or dangerous to human being. But so my question is that since this kind of real applications are so limited, is it necessary for the whole industry to spend much effort to standardize it? I mean, because we just put it into one of the triangle, one So is it necessary? That's my.
Do you mean if the standardization is necessary?
I mean, for this scenario, a deployment scenario, like the mission critical, because it's limited.
Yeah,
and it's not so.
Right.
Yeah.
Yeah. So. I mean, I definitely agree. I think it has to be. The techno-economics of this scenario haven't been really solved. How many applications are out there? Okay. It would be nice to have sub-millisecond delays in all systems all the time. But the question is, how much are we willing to pay for this, and what are the sort of the benefits from the applications, as you say? So I think it's absolutely valid question. And I mean, it may be possible that the solution is that we lower the delay somewhat. I mean, and how much lower should the delay be? How much can you do in autonomous processing, and how much network control is actually needed? I mean, we'll probably discuss the cars this afternoon or in the next session already, that maybe the car can handle the local traffic situation autonomously, and it needs only information about what the traffic looks like 100 meters away, and that information can be a second delay. That's not a problem. So it's really a matter of how much this millisecond delay actually contributes to your application, and it's not obvious, I would say.
Okay, thank you.
And before going to the next question, there, I guess we will not see everything go down to 1 millisecond in one go. Right? There will be an evolution also of offering a lower and lower delay, and then we will see where the demands takes us. And as we have seen with the data rates going up, I think we are now receiving data rates that we definitely not thought was possible or needed a few years ago. So I think we will see the development.
On the other hand, we need the high data rates because we want to be so flexible. So
yeah, exactly. We have used it for something. So before the coffee, a final question.
James. Yes, hello. James Cross, also from KTH. First of all, thanks a lot for this interesting talk. My take here is that if you think about these virtualized CPSs, first of all, this is a much bigger problem than just something being solved by the wireless community. Okay, that is kind of like accumulated here. Now, in that sense, I would like to challenge you a little bit, and maybe also everyone here, on the issue of standards. What you hear in this context these days much more is that there's going to be a creation of an ecosystem with all these different competencies coming in. And these ecosystems, in the best case, will come up with open source. And this will pick up momentum and then be the de facto solution that is coming up over the next 10 or 20 years for these systems. So, and I think that's something to discuss, really.
Yeah, I absolutely agree. I mean, I think that in the cyber-physical systems, we're in the same situation that we were in business computing 30 years ago. Every company built their own ledger and finance system from scratch, basically. But now there are modules available everywhere, and you use actually what you do is that you use standardized software and engineer your company around it, rather than the other way around. So it's. I think that could also be, and personally, I would say that in 50 years, the buildings will look the same. They will be standardized. So actually, we and the architecture will be adapted to the cyber physical system reality, rather than that we try to tweak the software for the buildings.
But then we need to be the first, right? We're coming up with the right one. And now the question is, who's we in this context, right? But that's the task here.
Yeah, the we is definitely more than the.
Who's we?
Yeah, it's definitely it's not just all of us here. I think it's society as a whole, or the industries in general, in plural. So I think that it's. I definitely agree. It's not just something for the wireless community to do. It's for everyone.
So, thanks a lot for comments, and thanks to Jens and all the speakers. So